It's a great pleasure to introduce Professor Mathew, who will be speaking about, who will be giving an introduction to derived algebraic geometry.
Yeah, okay, thanks a lot. Okay, so I was going to say a few things essentially from the book of Victoria Rosenblum. I guess this is volume 1, chapter 2. Okay, so first I wanted to say something about prestacks in general. So the setup is setup. So they want to consider a very general class of objects in derived algebraic geometry, and in particular, they want to sort of start by using the functor of points perspective. So recall that well, we have the notion, the classical notion of schemes. Right, this is classical schemes, and they're traditionally introduced as like locally ranged spaces, as a full subcategory of locally ranged spaces. But so we can also embed them. Sort of thinking about locally ranged spaces, which is not so it's not always going to cover some of the settings of interest in the seminar. So then you embed schemes into functors from rings. So just by remembering, so given a scheme, you can evaluate it on any ring. This gives you a fully faithful embedding, and you can characterize classical schemes as so they embed fully faithfully into such functors, and then you can impose some conditions on such functor to declare that it's a scheme. Okay, so then they make the following condition. So so first is that they want to replace stack. So stack is a functor. Let's say from coordinated algebras. Okay, so here we have a couple of comments. One is that animated. So in the setup, I guess K is a field of characteristic 0. Do we want to use 0 actually for the seminar? So
Well, if we need to make that restriction for today,
well,
force future speakers to relax, to explain to us how to relax the constraint, but
for the paper that we study in the seminar.
KRV.
Okay. Well, okay. So I mean, I think this definition is valid. So K is going to be a field. So let me just so maybe for this we'll say characteristic 0. And so then animated K algebras is so instead of working so the idea is that you want to replace that the notion of functors from ring results. You want to replace the notion of rings by animated rings or animated K algebras, where K is the base, in this case a field, and maybe in this case characteristic 0. And then you want to replace sets by NMR spaces or category spaces. And let me say that So I don't know if maybe this has been covered in the past, right? So this is So equivalent. This is also So you can describe this in a couple of ways. I mean, if for instance we're in characteristic 0, it's also the infinity category associated to connective commutative EP algebras over K. Well, okay, so it's that where you invert one inverts quasi-smooth. Okay, so you start with the category of connective. So in non-positive cohomological degrees, commutative DG algebras over K, and in that category you have the notion of quasi-isomorphism and then inverted quasi-isomorphism. So okay, so one can also describe this sort of more intrinsically using well, in that this is also the free subgroup composition. of the category of finitely generated polynomial rings. For K, and I guess this sort of precepted co-completion is what this animation terminology. Okay, so if K is a field of positive characteristic, then you probably don't want to consider this, but this is still a relevant definition. Okay, so a prestack is a functor from animated rings over K to M up. Okay, so right, so for example, right, so example is if you start with an animated K algebra, then there's a prestack. So R is an animated K algebra, then you get a prestack called spec R. So it's a prestack. So I guess prestack's called the category. It's the prestack sets A to comes from R. So we get an embedding of right. So the opposite of animated K algebra is embeds into prestacks just by the unit. Okay, so another example, I guess another example general is okay, so if X is let's say X is a classical scheme of finite type for K, then define X from the Durand prestack as follows. So okay, so this is going to be a functor from it's a functor from animated K algebras to anima, and explicitly it's going to set A to the value of X, not on A itself, but on so let's take pi 0 for H of A. So 0th homology of A. So that's a classical ring. And then mod out by the null points. So we also have this example of the Durand stack or Durand prestack, such that the A points of it are X applied to H of A reduced. Okay, so maybe this has been discussed in the seminar already. Okay, yeah. So
Still good to review some.
Okay.
Don't hesitate to.
Okay, so right, so there are a bunch of constructions that one can do with a bunch of basic constructions with animated rings that are also useful. Okay, so construction example. So example is that if R is an animated ring, so then you can form its truncations. I don't know if this is covered already.
Not in detail, so
Not in
feel free to
Okay.
go into it.
So okay, so if R is an animated K algebra, then one can form its truncations. So form its truncations. Tau less than or equal to n of A and a non-negative integer. So this is the truncation at the level, which is the truncation at the level of underlying objects of the derived category, or yeah. So implements tau greater than or equal to minus n homological conditions at the level of work. Okay. Right, and so then there's some useful definitions. So one is okay, so in particular you have tau less than or equal to 0, which is taking the underlying classical algebra. Okay, so then there's some definitions. So one is that we'll say that a prestack X is an truncated if it's determined by its values on n-truncated animated rings. If so X is a functor from animated rings to anima, and if X is left unsuspended, if X is left conic-second from the subcategory of n truncated animated rings, setting aside all animated rings. So it's sort of, so for example, if it's zero truncated, an example would be n equals 0, and then that would be saying that X is sort of, it's sort of formally determined by its values on classical K-optimers inside all animated K-optimers. And okay, so the terminology will say that X is convergent okay, so if for all animated K-algebras, the value of X on A, so it maps perfectly to the inverse limit value of X on less. Okay, actually, sorry, before I said this, I should have said that this notion of a prestack is flexible enough that it includes all like classical schemes, stacks, but also like say art, yeah, classical schemes or classical art and stacks. Okay, and so if you have right, so if you have like a classical scheme or classical stack, then it's going to be, and you bed it into this category, then it's going to be zero truncated. And essentially, so essentially, most of the objects one considers in practice will be convergent. And this is sort of useful because that just means that the value in an arbitrary animated ring is now determined by the value on truncated animated rings. And you can try to approach the value on truncated animated rings by starting with classical rings and then doing some sort of definition. So this is always going to be satisfied. Yes.
So do you think of an animated K-algebra as being represented by the DT algebra in particular?
Well, it can be. I mean, it can be represented by a DT algebra. Sure. Okay. So, yeah. I mean, well, I mean, if you did something like, so I think most objects that you might sort of write down geometric would be convergent. But okay, so let me write down an example of a prestack. So an example, right? So an example, one example of a prestack that you might consider is a prestack BGLN. Well, yeah. So let's say BGLN, or another example might be perf. Explicitly, this sends an animated ring, ring A. So the first one is sending A to BGLN of A, meaning, so take the anima of rank n projective modules A. Yeah. So an A module is projective. Well, this is really a condition on homogeneity, on the cohomology. So cohomology is projective of rank n as a module of the cohomology of A, and greater than degree 0. And so the second one is perf. So it's sending A to right. So it's the anima of perfect complexes, perfect A modules. And I guess equivalence is between them. So right, so these are going to be convergent, but something that's not convergent would be something like, so these are sort of, yeah, so it's geometric things. But something that's not geometric. Okay, so the above two, above two will be convergent. Above two are convergent. But an example of something that's not convergent would be something like send A to the groupoid of all A modules. I mean, that maybe you don't want to consider already for some theoretic reasons, but even if you said like countably generated, let's say countably generated, countably compact or omega 1 compact objects of, or you could say, let's say omega 1 compact objects for sort of set theoretic reasons. Right, so this is not gonna be, so this is not gonna be convergent because you can have an A module such that it's non-zero, but when you base change to any truncated thing, it becomes zero. So imagine some sort of two periodic, so imagine like A is, so imagine A is like K brackets T, where T is in degree -2 chromologically, and your module is K brackets T plus or minus 1. So then that's gonna be a module that base changes to zero after, under when you map to anything truncated. Okay, so this is not. Okay, so just, right, so the reason is that you can take A, well, imagine that the homology of A is K brackets T, where the degree of T is -2. So this you could represent by a formal DG algebra with differential 0, would be formal. Then you can consider the A module M. So the A module M, which is A brackets 1 over T. So it looks like a Laurent polynomial group. And then this has the property that if you take M tensor over A, how less than or equal to n of A, this is 0 for all of them. But it's not 0, so it's 0 when you do this, because then when you do this, you mod out by some power of T. Right. Yeah. Okay. Right, but so maybe I should point out that if you have any object which is so if you have anything, well, so spec R, so the example is that spec R is always equivalent. And in fact, any, say, n on stack, we haven't done that yet. But for example, any classical R stack, if you this way will be. So this is sort of a pretty mild condition. So I guess I was next going to say talk about finiteness conditions. Was that like almost 500%? Is that the?
No,
That was not. Okay, so that might be exactly. Okay, so this is some generalities on prestacks. There are also some finiteness conditions that would be relevant. Finiteness conditions either on a prestack or on an animated ring. Okay, so let me make the following definition. Okay, so we'll say that R is an animated algebra. So R is an animated algebra. We'll say that R is almost finitely presented. Well, I'll explain two equivalent characterizations. So the first one is that H0 of R is a finitely generated K algebra. And all the higher homologies of R are finitely generated as modes. So H0 is finitely generated as a K algebra, so it's going to go Ethereum, and then all the higher homologies are finitely generated as modules of H. So, or equivalently, so this is I guess non-trivial theorem. Non-trivial. So the theorem is that this also is sort of a categorical characterization of being almost finitely presented, and it means, and the condition is that, well, so given any filtered diagram of animated rings, which are all n truncated for some n, then homming out of R computes with that filtered code. So if A sub I is a filter diagram in animated rings, which are all n truncated for some n, then homming out of R. So. Then it becomes an animated tail for us from R into. Well, the other way. By. The equivalence to. R into full limit of. So this condition, right? So if you're working with ordinary rings, then an observation is that a ring is finitely presented. Okay, let's assume it's finitely generated for a field, but finitely presented in general, if and only if it's a compact object in the category of K present. And here you're requiring not that it's compact, but you're requiring that its n truncation for any n in n truncated animated is compact as an object of n truncated animated. So this is saying that L less than or equal to R as an object of animated rings. Truncated is. So I guess this is analogous to the notion of an almost perfect complex or a pseudo-coherent complex, which. Okay, and so then it's then it's a proposition that you can actually characterize that by looking at the level of cohomology. So a stronger condition that you could ask is that you would have this for all filter diagrams. So you could ask that it's actually a compact object of animated rings, but that's a much stronger condition. That's a much stronger condition that you won't be able to check just the level of cohomology. So I guess it will be the case in this example of quasi-smooth in this quasi-smooth setting that anyways we have interested in. Sure. Okay, and so then also you can right, so one defines that a prestack. So a prestack is right, so you would say that it's so you can make this kind of definition for a prestack as well. And okay, so a prestack X, let's say it's locally a finite type. Maybe locally almost.
Can we just ask a quick question? And you use the word almost here. This is the same almost or different almost? It's faulty. This is almost.
It's unrelated.
Unrelated. Good.
Unrelated.
Okay.
So almost is just referring to that it's not actually compact, but it's only compact when you n truncate for any. Right. So people also refer to almost perfect complexes. So so if you have a ring R, an almost perfect complex, something that you can represent by a chain complex of finitely generated projectives, which well, it's allowed to be unbounded, but only to topological minus. And so such objects are exactly ones that satisfy an analog of condition two. Okay, so we'll say that a prestack is locally almost a finite type. So again, this is from the two of them. Okay, so if so first of all, X is convergent, that's what it's written. And two is that it has this property. So X commutes with filter elements. Of animated rings where everything is uniformly n. Yeah, so I think again a lot of the examples that are that I think would be relevant to the seminar will have this. Right, so these conditions, right, so maybe I should just say that these conditions imply that a priori a prestack is something that you define on all animated rings. These conditions mean that X is actually determined instead of evaluating all animated rings, it's going to be determined by its restriction to rings which are truncated and almost finally presented. So it's going to be just right, this is comment. Mark is that if X is locally yes, so to use your prediction, LAFT. Right, so then X is determined by its restriction. So the X is a factor on all animated rings, but it's actually determined by its restriction. Two animated rings, animated K-algebras, such that one is that R is n-truncated for some n. And two is that, okay, so it's n-truncated and it's almost finally presented in the above sense. So, right, so the reason is that if you want to know the value on any n-truncated K-algebra, you can write it as a colimit of things which are compact in n-truncated K-algebras, animated K-algebras, which are particular almost finitely presented. So then X extends well, basically by the passage to, well, since X is required to commute with filtered colimits of n-truncated rings, then this is gonna, once you know its values for here, then you know its values on all n-truncated rings. And then because X is also required to be convergent, once you know its values on n-truncated rings for all n, then you know its values on all n-truncated rings. So there's sort of both the left and the right conic extension, left conic extension from going from sort of finite things to infinite things, and then right conic extension for taking the limit along with. Okay. Okay, so yes. Say
for prestack, we use like local almost and either it's similar to a cell structure, like constructing like we could like a really complex with some.
yeah, so this condition of, well, so for an animated ring, oh yeah, I guess I should have said the, so in particular, if you have, well, maybe I should have first said the thing that, so if you have an almost finitely presented algebra, then spec of it is locally almost finite type in a sense. Yeah, okay, so maybe I should write some examples, but the other is that being almost finitely presented, so the analogy is that it's, the analogy would be that if you have a homotopy type anima, then you could represent it as a CW complex where you have finally many cells in each degree. Where you have infinitely cells in total, many cells in total, but finally many in each. I think all the examples I've written on the board besides, well, so the examples written on the board besides that last one, of course, are going to be LN. The examples of like so PGLN or perf are LN. Okay. All right, so maybe next I wanted to discuss, well, so probably one doesn't want to consider all prestacks, but wants to also impose some sort of descent condition. So I wanted to say something about flat descent in this context. So let's say I wanted to define the flat topology for animated rings. So this was okay. So all right. So let's say I have a map of animated rings. So let R to R prime be a map of animated rings. We say that okay, so for animated K-algebras, we say that it's flat. Say that F is flat. Okay, so we have two conditions. So one is that it's flat on zeroth topology. So H0 of F from H0 of R to H0 of R prime is flat. And two is that on all the other chronology groups, it's just sort of induced from. So the way to write this is that the map from so H0 of R prime tensored over H0 of R with H star of R. This maps to H star of R prime. This map has to be an exponent. Here, so in other words, what happens on the higher homology groups is determined by what it does on groups. Okay, so this is equivalent. So this is equivalent to the condition. Mark is the flatness of F. So F induces an extension of scalars functor from mod of R to mod of R prime, and it's equivalent to that being T exact. It's equivalent. So have extension of scalars from mod R or D of R, mod of R prime. And both of these carry natural T structures, and the condition of flatness is equivalent to upper star being T exact. It's always right T exact, but T exact, that's the same as flatness. Okay, so then we'll also say that F is smooth or étale or faithfully flat if it's flat and the same condition holds for H0. So definition, F is faithfully flat or let's say étale so if F is first of all flat in the above sense, and on H0, it's either faithfully flat or étale. Okay, so one remark is that this notion of étaleness behaves very well in the following sense. So a remark is that so the category of étale are algebras. Infinity category of étale are algebras. So if you have an étale R algebra, in particular, it gives you an étale H0 of R algebra by definition. And the claim is that that's actually an equivalence of categories. It's equivalent to the category of étale H0 of R. So in other words, the étale side of an animated ring is the same as the étale side of its zeroth cohomology. So this is analogous to the more classical fact that the étale side of a classical ring is the same as that of its reduction. And so, okay, so in particular, it's a one.
There is a sort of analogy between taking H0 and taking the reduced part
Yes.
of a scheme.
Yes. So analogy, like that. So analogy, the map, so you have a truncation map from R to L less than or equal to R. This is analogous to the map from a classical ring to its quotient mod the node radical. Quotient, well, let's just say mod and node. Okay, so Okay, so this defines a Brownian topology on affine direct teams, or on the opposite of animated rings. So we talk about having flat descent or a tall descent. Okay, so this defines a Brownian topology. And we scale this. So it makes sense to ask for when a prestack satisfies a tall or flat descent.
So is there a local finite resolution or type of condition here too, or
Well,
that you impose for this, for the site? Or
well, I mean, sorry, I'm not sure.
or like, what are the, like, are the covers just flat jointly survective maps?
Yeah,
Oh, okay, so there's no, it's not like FPPF,
I'm not sure I understand.
like. Okay, but the covers are just flat jointly survective maps, for instance. Okay, thank you.
Yep, so yeah, so explicitly. So explicitly. A prestack. X from animated scale plus. Say that it satisfies descent. Yeah, so I mean, okay, you can also define a variant of this where you say F and PF instead. So just same condition, but you require the map on H0.
So all the finiteness stuff that you see at PQC, at the tall, all snuggled in just the.
Yes. So yeah, so very explicitly, what you need is that X of, well, first X will come in with quasi products. X of R1 cross R2. It's equivalent to X of R1 cross X of R2. And two is that if you have, okay, so if you have a faithfully flat map, so if R, well, if R to R prime is faithfully flat and animated scale comprised. But then, then the condition is that the value of X on R, well, it maps to the inverse limit over the simplex category, value of X of R, value of X of X R prime tensor R prime. So you form the check curve of the map R to R prime, and you get a big simplicial or a co-simplicial diagram of animated K algebras, and you want the value of X R to be the limit of that. Okay, so there's a theorem here. So theorem. Right. That right, right, so one reason this is useful is following theorem that that taking modules, so sending an animated ring R to modules over it. So again, it's the right category, that it satisfies flat descent, in fact, flat hyper descent. So R comes to R satisfies flat descent. Descent, well, it uses essentially the fact that you have a T structure on R modules, and well, particularly uses, I guess, an elaboration of some of the same things that you use to prove flat descent for classical modules.
So this classic thing that would take us, reduce the case of a section.
Yeah.
And then, okay, yeah.
Yeah, so in particular, right, so you use the fact that that tensoring along the flat map is T exact. Okay, so right, so things right. Okay, so, right, so another remark is that one reason to impose this and is that, right, so you want to remember, you want to form columns, probably when you want to form columns, you probably form them not in three stacks, but in stacks. So we want to form columns. Yeah, so I guess we'll say that something is a stack if it satisfies descent, either for the flat or the intel topology, depending on the condition. Setup you're considering, and typically when you want to form a column, you'd want to form it in stacks rather than three stacks. So, right, so if you think of it like a Zariski open cover of a scheme, like if you want to think of P1 as being moved from two copies of A1 along GM, but that's not a column in three stacks, but it is a column in stacks. So typically we want this condition.
What would the color prestacks look like in that example you just said?
Well, I mean, you would the column in prestacks would just be the pointwise column.
Okay.
So it would be like our points would be like maps into P1 that factor through one of the open, right? So one of the
Brilliant. Oh, okay.
So you want it, so when you actually, right, so when you form, so if you think of affine schemes as prestacks and you're moving to get a more general scheme, then that's a column, not in prestacks, but in stacks.
Okay. That example is perfect too.
Okay, so then let me define quasi-coherent shapes. Okay, so so let's say X. So X is a sorry, so maybe before I do that, let me just give an example. So let me just give another example of how you would form a column in a stack or three stacks. So for example, you could have something like a flat groupoid, but you could start with schemes and you could have like a flat groupoid in schemes. And then you want that to represent a stack. But you would do that by forming the column in stacks, again, rather than three stacks. So for example, the stack PG is like column of point by G, but that's a column, but it's a column, like it's a column of the sequential diagram that you write down, but it's a column in stacks. Okay, so let me just make a definition. So definition now. So given a free stack X,
Stacks and then stack.
yes, well, I mean that's how you form a column in stacks. Oh, you first form it in free stacks, so then you should okay, so given a free stack, so then we can, there's a notion of a quasi-coherent sheaf on it. So so define quasi-co of X. So that's the inverse limit. So overall animated ring, so you look at all of, so anytime you have a map from stack of an animated ring to X, then you have the category of the affinity category of R modules. And then you take the inverse limit of all of these as the range of all. So in other words, quasi-co is a functor from, okay, so I said it a little bit informally, but quasi-co is a functor from prestacks to categories, so let's say presentably symmetric monoidal categories. And explicitly, it's the right common extension. Okay, sorry, maybe I should have said. Sorry, maybe I want to say prestack. So it's the right common extension. It's the right common extension of the functor that sends a ring R, an animated ring R, to modules. So a remark is that basically by this theorem of flat descent, the notion of quasi-coherent sheaves, it only depends on the underlying stack. So the remark is that X, well, quasi-co of X, right, so is defined for free stacks but it's an invariant, it factors from the stackification. Quasi-co x equals quasi-co stackification. And so this is useful because, right, so we present a colimit, well, if we're representing a stack by some sort of colimit in, well, it's some sort of colimit of a diagram, then it tells you that you can use that to compute, well, so explicitly, if X is like the colimit in stacks, it's a diagram, then you can turn that into a limit. And the quasi-co, that stack colimit is the inverse limit of quasi-co of each of the constituents.
So in particular, this would give us something like maybe in scheme, or is that the wrong way? We getting the wrong kind of limit there. This would give us the notion of quasi-co in scheme. Or something.
Oh, sure. So if you have an in scheme, so example, right? Yeah. So example, if you have an in scheme given by a filtered full of schemes, x1, x2 to x3. So diagram of schemes, and you take the colimit x colimit of the x sides. So schemes, then this is an in scheme, so it could be like everything scheme. Then quasi-co of x infinity is the inverse limit of quasi-co of x. Well, basically by construction of quasi-co, that it's
So this is a non-happy way to define the quasi-coherent sheaves in the affine cross volume. In particular, this is maybe we call a lower tech description than in the past.
Sorry, when you say stack here, you mean restack satisfying the flatness descent?
Yes.
Okay.
yeah, very sure. That. Stack. And okay, so maybe you would consider spirit where you require a BF descent or a tall descent.
I guess just in the definition of flatness, I'm kind of wondering what the second condition is doing for you. Like, what would be sort of wrong if you just define flatness as flat on H0?
Okay, so I think part of what you want here is you want it to behave well with the T structure. So if it's just flat on H0, then something like well, something if you have then the map from any animated ring to its zero truncation would be. And thinking about that as sort of like motioning out by some sort of so we don't want it, but maybe I should justify a little bit of why we want this yeah, so we said that being flat in the sense is the same as being T exact. And okay, so yeah. Okay, so example, so let's say X is so it's a stack and it's represented by a flat groupoid in affine space. So it's a limit of a flat groupoid okay, let me just say affine space. Okay, so I think the conventions of the most one, this would include like a one Artin stack. But okay, so I think you can also iterate this and continue, but let's sort of start with this. So it's some flat groupoid, let's call that Y bullet. So Y bullet is a simplicial, it's your simplicial object in affine derived schemes. And well, okay, so the transition maps are flat. Okay, so then you get the quasi-co of X is well, it's the inverse limit of quasi-co Y bullet. And, right, so I guess the observation is that, yeah, so the observation is that quasi-coex is gonna obtain a T structure in this context. So this observation, quasi-coex. So the point is that in this totalization, or in this inverse limit, because of the flatness, you can, so quasi-co of like modules over an animated ring comes with the T structure. And if the transition maps are T exact, then you can put a T structure on the inverse limit. So it inherits a T structure. Where an object, so F in quasi-coex is either connective or co-connective. If its pullback to y0 is connective. So because everything in question is T exact, you can define a T structure on the inverse. You can define a structure on the inverse limit such that either being co-connective or connective is something that you can check on the individual. Okay, so maybe let me give an example. An example is, right, so let me do that example of BG. So again, BG, G is an affine scheme. So in this case, so quasi-co of BG. Right, so sorry, so also, right, so what is the heart of this T structure? The heart of this T structure will be sort of classical quasi-coherent sheaves on the underlying classical stack. The Abelian category of quasi-coherent sheaves on the underlying classical stack. Okay, so if you have an affine group scheme, then in this case, the point is that quasi-co of BG, well, it's the left completion of the derived category of G representations. So if you have BG where G is an affine group scheme, you can form quasi-co of BG by this general machinery. So it's some inverse limit of categories. And the claim is that you can also describe it in more classical terms. So you have the notion of a G representation, and you have an abelian category of G representations, and then you can form its unbounded derived category. And then the claim is that it's that up to left completion. And I guess if G is finite type, then if you're in characteristic 0, then I think this is already left complete. But if you're also right, so if you're in characteristic P, then already like GA representations. Okay, so right, and so the reason for this is right. So there's some relatively formal reason for this, and there's a characterization of when something is a derived category. Right, so if C is a let's say it's a presentable, so let's say it's a stable infinity category with the T structure. Let's say the T structure, so it's presentable and the T structure can be used with colimits. So let's say so that means it's rotation stable, and we call this rotation stable. Then there's a characterization of, so then you have then you have the heart, which in this case is just classical G representations, and there's a characterization of when so there's a characterization of when it's actually the derived category of its heart, maybe up to left completion. So let's see if C so suppose the following, suppose for all X in the heart, there exists an embedding X into X prime in C heart, such that for all Y in the heart, we have that Xi from Y into X prime equals 0, for either. So then C, again, up to these issues of completion is exactly the derived category. Oh. Okay. Right, so let me just finish this. So then C, if you look at objects which are just bounded away from minus infinity, it's the same thing as the derived category of C for, again, bounded away from minus. So you have, so this is the key sort of, well, it's kind of like embedding into an injective object that you need to guarantee that C agrees with the derived category of its part, again, away from homological minus infinity. Now, just the comment was in, okay, so what I unfortunately just erased, you don't in general get the literally the derived category of its part, because you know that quasi-co, if you construct quasi-co in this way, it's automatically left complete. So quasi-co as constructed in this way is automatically left complete, because it's the inverse limit of like a diagram of left complete things, namely modules of row. And maybe this is a good point for a break. I guess we're supposed to 10-minute break. Is that
Yep,
correct?
that's standard.
Okay, so I guess if I would say something about quasi-smooth animated wings and the cotangent complex, and say something about the singular support for ind-coherent. Okay, so first let me say quasi-smoothness. Smooth rings. Okay, so the idea is that this is a derived of the notion of a local intersection. So definition will say that an animated ring R, animated algebra, is quasi-smooth. So we'll say that it's quasi-smooth. Okay, so first it's going to be almost finally presented. So I'll do some equivalent characterization. So one is that R is almost finally presented. And two is that if you take the cotangent complex of R over K, so this is an object living in the connective derived category of R. Right, so it's going to have Tor amplitude. It's going to have Tor amplitude in -1 constant. Something that I should have said earlier is that if you have something which is almost finally presented, then its cotangent complex is an almost perfect complex. Okay, so here you're required that it actually has Tor amplitude at -1 constant. Okay, so what is the basic example of this? Right, so example is, let's start with a polynomial ring. X1, X2. And now let me mod it. So I guess a basic example is a complete intersection. So let's take a polynomial ring on variables X1 through Xn and mod out by one with Fm. So polynomials where F1 through Fm form a regular sequence. Right. So in this case, R is quasi-smooth. In fact, the cotangent complex of R over K, you can describe it as the following two-term complex. So first you have the direct sum of R times D pi, and the direct sum of R times, let's say, D K J from 1 to M. E sub J is going to map to the differential of F sub J. Here, so consider right, so the differential of F sub J is a living, well, it's going to be a linear combination of dx1 through dxn and with dx1 through dxn, and then map that over. So it's this so the tangent complex is given by this complex. Okay, but right. But in general, so in general, if you don't assume that F1 through Fn form a regular sequence, then well, then you should form the derived version of this. So this is quasi-smooth, and this is a classical intersection. So another example is if you don't assume that it's a regular sequence. So then you can form K brackets now mod out onto derived sets by F1 through Fn. And so by definition, that's a derived tensor product of K brackets x1 through xn with K brackets y1 through y sub n, where the y sub i's are mapping to the or y sub j maps to okay, so right, so this is explicitly this is the causal complex as a chain complex. This is a causal complex on F1 through 3. Okay, so then this is quasi-smooth. And right, so if F1 through Fn does not form a regular sequence, then this will be non-classical. Sort of genuinely and so has the cotangent complex been covered?
No, it is not. We've discussed the cotangent in a sort of my very naive way for BunG only, but so if you'd like to actually go, you're welcome to, but if it's taking you too far, whatever, you need to do judgment, basically.
Well, okay, so I can say something about that. So maybe let me just continue. So example is right. So example is you could take right. So you could take well, you could take n equals 0, and then you could form the ring, which is K. Well, the derived suspension of the polynomial ring. Well, okay, so let's say K brackets x1. And so you can form this derived tensor product, and this gives you an animated ring. Well, explicitly, it's the free animated ring, animated K algebra on n classes n degree minus 1, and its homology looks like an exterior algebra. Exterior algebra on n generators. Those n yeah. N classes and so the n classes that you get from in okay, so this is an example of a quasi-smooth algebra, and right, so any quasi-smooth algebra, it'll automatically be okay. So maybe I should say the theorem. So for the theorem is that basically this is the example. So any quasi-smooth ring, at least sort of Zariski locally, is a Zariski. So any quasi-smooth algebra
So this is a bit like any smooth scheme, it's a call locally affines.
Yes. So geometrically, you have a map of smooth schemes, and then you're supposed to take the fiber in the derived sets over a point. So geometrically, one has a map mean, smooth schemes. And one takes the derived fiber over. Yes.
So does open immersion just mean the underlying map on classical schemes is open immersion?
Yes, and then it's well, but then it's also induced, then it's flat in the sense. So you have the notion of an open immersion of so yeah. You have a notion of like an open immersion of animated rings. So it's an open immersion on underlying classical rings, and then it's flat.
So that like you're part of this.
Yeah, you're perfect. Okay, so.
So in that case, what is the complex?
Well, it's also gonna be, this. Yeah, because the idea is that the cotangent complex will behave well with respect to forming a mapping fiber. Well, the idea is that if you have, well, I guess the idea is that there'll be some sort of there's a transitivity triangle for the cotangent complex if you have a map. And this one is. All right, so, maybe I should say, maybe I should just say something with the complex real quick for prestack. So it's not going to prestack, you could also cancel the bar. The notion of a cotangent complex, so I guess, so it's going to be a definition. So the cotangent complex is a construction. Right, so I mean, this is supposed to be the derived version of the cotangent bundle. So in particular, for something smooth, it literally will be the cotangent bundle. It's a construction that makes sense. Or a prestack. I mean, it doesn't always have to exist, but at least it makes sense. Prestack. Again, I'm thinking of that as a function from animated algebras. So the idea is that if I have an element eta in X of C, where C is an animated ring, well, I can consider how this point eta deforms along a square zero extension. So consider the functor which carries a C module M to well, I'm going to take, so if I have a C module M, I can form the square zero extension of C by M as an animated ring, and this maps to X of C. And I can form the fiber of this map for the distinguished point eta. So in X of C, I have a distinguished point eta, and I can sort of ask how it deforms along square zero extensions. Namely, I can ask how, like, what is the fiber of this map of M? Okay, and right, so if this is representable, so this is a buffer on, let's say, connected C modules, and if this is this is a buffer from connected C modules to anima, and if this is co-representable by an object N in all C modules, then you call this the cotangent complex of X at the point eta. So eta is a map from stack C, right, into X, and we're getting a C module, and we're thinking of, and so that would be called the cotangent complex of X at that point eta. So it may or may not exist, but if it does exist, we call it. So, okay, so this is the cotangent complex of X at a given point, which is a C, an object of C modules. So in favorable situations, you can glue them over all points, and then you would get a quasi-coherent sheaf on X. So in favorable situations, so for sort of reasonably nice X, so for example, for like an Artin stack or an n-Artin stack, the cotangent complex to X will exist at all points, and they'll be compatible with each other. So a cotangent complex to X exists for any eta, and then they'll be compatible with each other. So let me just point out that this is a property and not a structure. The cotangent complex either exists or it doesn't. You don't sort of construct it, because this is really a property that the functor is co-representable. And then the compatibility is also a property. If you have a cotangent complex at every point eta, then there are going to be compatibility maps between them that you have for free, and then you can ask that those compatibility maps are equivalences. And so in that case, you'll get a cotangent complex for every such eta, and they'll be compatible, which is to say that you'll get an object of quasi-coherence. So in particular, for an affine derived scheme or an animated ring, you have a theory of the cotangent complex, and it is characterized by this condition. Right, so basically, the cotangent complex of an animated ring R is controlling how you can map from R into a square zero extension, C directs on M, based on how you can map. All right. So maybe in the remaining time, I wanted to say something about.
Actually, how did you smuggle in the square zero in that definition there? Is that just because it's C plus M?
C plus M, yeah. Okay, so I guess I thought I would say something about the singular support. Perhaps that would be, yeah. Okay, so I guess also this I think is gonna. Wait, so I guess in the context of the talk sheets, this will appear in next week's talk.
Happening, more the merrier.
Okay. All right. Okay, so the setting is going to be, so maybe I will just do this for affine derived schemes. So let me say something about the singulars. So, okay, so let Z spec R be an affine derived scheme. Okay, yeah, so it's fine. Right, so then okay, so then Gator and Rosenblum, following earlier work by Henry Prestack, consider this category ind-co of X. So consider ind-co of C or ind-co of R. And by definition, this is the int category. So by definition, this is the int category of the infinite category of coherent R modules. So I guess this is. Let me tell you what a coherent R module is. So an object M and D of R, or sorry, in mod of R, to that notation, is coherent if right, so if it has a its cohomology is bounded and each and finitely general. So if well, I could just say it very quickly in that the cohomology of M, global cohomology of M, is finitely generated as a module over H0. So probably this has been covered in the seminar past.
So
Yeah, I mean, it sort of, it's been mentioned what these definitions are, but feel free to go and
Okay.
detail if you'd like to. Yeah, I mean, we've not, for instance, defined it nilpotent singular support ever before, so this is coming this.
Okay, so, right, okay, so recall that if you have a regular ring, so if you have a regular ring, then, like a regular classical ring, right, so then being coherent in this is the same as being perfect. Then for an object of D of R, it's perfect if and only if the total cohomology is finitely generated. But that's not true if you have a if you have a singular ring. And so instead, okay, so instead of considering perfect R, you consider this category co of R, which is exactly those objects whose total cohomology is finitely generated for H0 of R, and then you form its end-completion ind of R. Okay, so let's see, so it's very possible and develop okay, and so then you can glue this to define it for for a more general scheme. And sorry, did I? Okay, sorry. So sorry. I need to assume that R is almost finite, almost finitely present. But I want it to be right. So I want H0 of R to be. Okay. So right. So it's also want to study this category of incoherent sheaves, and in particular, they set up six function formalism for this as the derived scheme varies. But six function formalism. So for
Only one derived algebraic geometry, that node is essentially the whole setup of encompassed, and that's the major subject of the first volume.
yes. Yeah, so in their okay, so right, so the idea of the singular support. So I guess right, so I guess this is following the paper by Rington and Kingsbury, is that you can define certain subcategories of ind-co. Well, you can define certain subcategories of ind-co of R if R is quasi-smooth. So right now, define certain subcategories of ind-co of R where R is quasi-smooth. R is quasi-smooth. And make it. And right, so these are going to be examples of localizing subcategories. Okay, I just start by replying the definition. If right, so if C is a right, so C is a, let's say it's a presentable stable infinity category. So a subcategory of C is called localizing. So a subcategory E sitting inside of C is localizing. Right, so it's closed under colimits and desuspension. So it's stable and closed under colimits. You have stable and closed under colimits. So a simple example is So inside D of Z, so you can take C to be D of Z, and you can define D to be the subcategory of objects such that when you invert P, you get 0. So that means that P acts locally nilpotently on the cohomology. It's the localizing subcategory. And so this is often how you can define a localizing subcategory. You can impose some sort of local nilpotence condition on some endopoints. So in particular, okay, so you could generalize this. So right, so generalization of this example. So if if X is a QCQS scheme, derived scheme, and Z sitting inside X is a closed subset. So define a localizing subcategory. Quasi-co if X sitting inside quasi-co of X, and it's going to be all those objects which are set theoretically supported on Z. Supported on Z. So right, so X is spec R, and Z is the vanishing locus of some ideal I. Right, so in this case, quasi-co of Z of X is going to be those elements, going to be those R modules, which are such that any element of I acts locally nilpotently on that. Be those M mod R, such that I guess M again 1 over F is 0 for all F belonging to this ideal. And this only depends on the ideal sort of up to radical. So it only really, so this is really a condition only on set Z, the ideal. Okay, so this is just a generalization example, and so this is going to give you a localizing. Okay, so right, so I guess the idea here is that you can so for a quasi-smooth animated ring or derived scheme, you can define certain localizing subcategories of ind-co of R, not only in terms of like subsets of spec R, but subsets of this. Okay, so I guess in the very convincing paper called Sing of Z. So this so maybe I should find that. Okay. Right, so maybe I should remark that so maybe let me just give an example that predated the history paper, and this was work of Benson, Iyengar, Hausa. So I guess they were working in positive characteristic, but essentially they considered ind-co of K brackets G. Well, okay, let's say K brackets G, where now K is characteristic P, and G is let's say it's an elementary abelian P. So it's like C mod P to the. So take the group ring on an elementary abelian P group, In other words, it's kind of like the derived category of representations in this group, but again, we're taking coherent objects and then taking in. So essentially, they consider ind-co of this. And so then they actually so they classified all localizing subcategories of this ind-co. And so so the point is that if you take spec of this ring, it's just a point, because this algebra is all nilpotents, because it's a group ring on a P group and characteristic. But on the other hand, so on the other hand, if you take the cohomology of the group cohomology of PG with a coefficients, this is now a rather large weighted ring. It's a polynomial ring on n generators. And they observe that whenever you have, so you consider this ring cohomology of PG with k coefficients. So so inside here there's a polynomial ring. This contains a polynomial ring on classes x1 to xn, where each xi goes to cohomological degree 2. And so then the observation is that if you have a subset of, if you have a closed subset of the affine space of an, which is GM equivariant, so in other words, it's defined by some homogeneous polynomial equations, then you can make exactly that definition. So so given a homogeneous ideal, I in this ring, then you can define a localizing subcategory of ind-co. So then you define a localizing subcategory of ind-co. And so let me just elaborate. So the idea is that so this is the cohomology ring of K, which is endomorphisms of the unit object in ind-co of K brackets G. So these cohomology operations are endomorphisms of the unit, but they induce endomorphisms of any object. You tensor with that object. And then so you get natural degree 2 endomorphisms of any object, and you can define a localizing subcategory for a homogeneous ideal by saying that those endomorphisms are all locally known. So explicitly, so explicitly, so the cohomology of dt with the K coefficients, it naturally maps to the ring of, let's say, graded endomorphisms of any object M, because this is endomorphisms of the unit object, and endomorphisms of the unit object act on any object, and can ask that any, let's say, f and I, which is homogeneous, satisfies n adjoint 1 for f is to define a localizing subcategory of ind-co of K brackets G by, well, for this homogeneous ideal I, you require that any element of the homogeneous ideal is locally nilpotent on the cohomology. And so they prove that basically all localizing subcategories, well, I mean, they rise in this or sort of complementary forms. Okay, so this is kind of, I mean, so this is so it's quite similar to the construction here. It'd be a characteristic 0 and it'd be a more focal thing.
Yeah, we didn't do kind of
Well, I mean, okay, so this has some additional exterior generators. Those are no problems.
Oh.
Okay, so
Wait, so these are the open localizing subcategories, is that?
yeah, so I think they show that the localizing subcategories are the same as the points of the subtheoretic or scheme theoretic points of spec of that one GM. So they're yeah. wait. So, sorry, so. I should, Okay, so the setup is as before, Z spec R is a quasi-smooth derived scheme. And okay, so again, one wants to define some localizing subcategories of ind-co of Z. Well, yeah. So right, so the construction is to so then they define a scheme, and really we're only going to care about this as a reduced scheme. It's only going to be relevant as a reduced scheme. So I'll call this thing of Z. And so this is going to be a scheme that lives over Z, such that the fiber of this map at any element Z and Z is exactly the so it's a cotangent space of exactly H1 of the cotangent space. Whoops. So okay, so it's going to be H H minus one of, well, okay, so take cotangent complex of Z and then restrict that to. Oh, sorry, let me make this a little bit more explicit. So they define a scheme living over Z whose fibers are vector spaces, and the fiber at a point in Z is so this is like some sort of version of the cotangent bundle, but instead of, well, the fibers being cotangent spaces, the fiber at a given point will be H1, so that H1 of the cotangent complex of Z base chain should have. Okay, so
This is some one truncated cotangent space.
yeah, so that right, but the thing is that the cotangent, because Z is quasi-smooth, you take the cotangent complex of Z and take the fiber at any point. It's only going to have cohomology in degree 0 and degree -1.
I see. This really loses very little.
Yes. Okay, so right, so let me explicitly. So explicitly, okay, so suppose that this quasi-smooth derived scheme Z is the fiber. So it's the, well, let's say you have a smooth map from U to V. So let's say U and V are smooth, and I have some map. I can call that F, and then I have a point star inside here, and Z is the pullback. So it's F inverse star. Okay, so and here you're forming the pullback in derived scheme. So any quasi-smooth derived scheme, it's locally the fiber. I mean, right, so by the way, earlier, it's locally the fiber of a map that means classical smooth schemes. The fiber is taken into the premises. Okay, so right, so then explicitly, so in this case, this thing of Z, it's going to consist of, well, first of all, a point. Right, so first of all, it's going to consist of a point X in U such that F of X is a point. Right, so that's the definition of Z for us. Okay, sorry, so sigma of Z is really, I guess I should say it's really living over the underlying classical schemes. So sigma, the space sigma of Z is really only going to be used as really as a topological space. Okay, but then also we're going to take an element C in the cotangent space. So this is now just a classical cotangent space. So classical cotangent space at the point. So maybe I should call this point 0. Oh, let me call this point 0. So an element in the classical cotangent space of V at the point 0. And if you have a cotangent vector, you can pull it back, and I want that F upper star of C. So, okay, so explicitly we're saying that if Z is a fiber, the map of smooth schemes to B, we're saying that a point of sig of Z, well, you have essentially have to give, well, first you have to give a point up here, and then you have to give a cotangent vector. You have to give a cotangent vector in the specified point here, such that this cotangent vector pulls back to 0. Okay, and so that's essentially because the cotangent. So the reason for this is that the cotangent complex of C is going to be the cofiber of the classical cotangent. I guess the classical cotangent space over here pulled back to the cotangent space. So this is C. Okay, so another definition. Yeah.
In H one is will also classify deformation, right? That have anything to do.
Well, I mean, this is basically like it's basically giving you the cotangent complex, but you're looking at H1 of it.
Yeah. Oh, sorry. Yeah. It's
Okay. Well, maybe this is also helpful. So another definition is, so we have the cotangent complex of V as an element of so per C, and as part of to the degree 0 and -1, we could also let sort of the derived version of the tangent space to be just the dual of this, the linear dual of sub C. Comes from C. Okay, so now this is going to have term amplitude, I guess, homologically in degree 0 and 1. So if you shift, so you can shift it by 1, and then you'll get something. So then sig of C is so it's a relative spectrum of sim star of T16. Reordering Z class. Okay. So say. Okay. So given. So I guess the basic construction is given a closed subset Y inside sigma C, which is closed and also GM equivariant. I mean, right, so this is back of some graded rate, so just wanted to be defined by a homogeneous ideal, then the construction is that you get a localizing subcategory moving into sub Y of Z sitting inside and of Z. So whenever you have a geometric canonical subset of this space in C, then they define a localizing subcategory of ind-co of Z in a way that's well, sort of reminiscent of the above. They have the additional to do. Okay, so we define a localizing subcategory, and yeah, so maybe I should say something about it.
So a geometric variant subset of something that you find looks like a family of cones or something like
Yes.
that. Okay. Family of cones of
Yes.
with respect to that family of codes.
Yes. So they define these various subcategories, and let me just explain the characterization if okay right, and I guess okay, so if F is actually in co of Y, sorry, co of Z, then I guess it'll be a minimal Y such that this is true, and that's called a singular support. Okay, so there's the following characterization. Sorry, let me put it this way. So if F is in co of Z, then there's a minimal Y. Minimal sub Y such that F is an ind-co Y of Z, and this is called a singular support. Okay, so right, so maybe the first example is that if your object is actually perfect, then the singular support is going to be contained in the zero section, and it's just going to be the set theoretic support. So so it's just going to be a subset of Z, which is the usual support. So this is some sort of refinement of the usual support.
So say it one more time. When under what circumstances let's just be the classical?
So okay, so the first example is that if right, so if F is actually in perf of Z, so that's a subset of co of Z. Oh yeah, so right, so because right, so if you have something which is n truncated for some n, so for example something which is quasi-smooth, then perf sits inside co, and if something is perfect, then the singular support is just a support. Then the singular support of F it's contained in the zero section, so it's just contained in Z classical sitting inside this sig of Z, and it's exactly the support. It's a usual set of things. Also in the sense that it was discussed earlier. Okay, so yeah, there's some sort of finite support. And there's the following characterization in general. So if F is in co of Z, okay, so let me suppose, right? So let me suppose that we're in the setting, in the special setting earlier. So suppose, right? So suppose Z is equal to F inverse of 0, where F is a map from V, smooth, and 0 in V as earlier. So then you could ask, what does it mean explicitly for an element to be in the singular support? Okay, so then as before, so let's consider an element C in this sig of Z. So as before, it's given by right. So in particular, right. So in particular, we have so consider a point of of single. So explicitly, that means a pair X in U and a point C in tangent space at 0 of V, and F upper star of C is equal. So then the claim is that this point, so here, this point P. So then P is not in the singular support of F. If and only if the following happens. Okay, so then there's a characterization of okay, so the singular support of F again, right? So that's a subset of C. And so you can say what it means to not be in the singular support. So explicitly, take a function G on U. Such that the differential of G is equal to so such that first of all G of 0 is equal to 0, and the differential of G is equal to this element. The differential of G at 0 is equal to this G. Okay, so if you have this, then okay, so then when you pull back so then X. Okay. G of G is defined on. Oh, thank you, yes, thank you. Take a function G on V. Yes, thank you. Such that the differential is equal to C. And then the condition is that. Okay, so then the condition is so P is not in the singular support. So F is living on the preimage of 0 inside U, and you can also. Okay, so how should I say this? So X equals F inverse of 0. That lives inside G composed with F. So G composed with F is now just a function on U, and I can take the preimage of 0. So this is now hypersurface. This is now a hypersurface inside U, which is singular. And the condition is that F is living on X, but if you push it forward to here, then it needs to be perfect. Right, so F is perfect on G composed with F inverse of 0, which is a singular hypersurface inside U. So basically, it's saying that you can check the condition of a point not being in the singular support. You can check that condition by asking whether your object, which is coherent, whether it's perfect on these so on hypersurfaces on various hypersurfaces of U that contain the object that you started. So I guess I'm essentially out of time. So maybe I just say something about where this construction comes from, and then I'll stop. Yeah, and I guess maybe for this also for this maybe I probably want C to be non-zero. Okay, so where does this come from? So where does the construction? So the construction. So it uses, well, so it's the same kind of idea that there are certain natural operators on any object of ind-co of Z, and then you can ask whether those operators are locally nilpotent. So the construction uses the Hochschild homology. So you take the Hochschild homology of this, right, so of this animated ring R that you were considering. So consider the Hochschild cohomology over K, and the Hochschild cohomology naturally acts, well, it gives you natural endomorphisms of the identity functor. So I guess by construction, it's endomorphisms of the identity functor. So the Hochschild cohomology of R naturally maps. So it's endomorphisms of the identity functor on R modules, in particular on coherent R modules, and then on ind-coherent R modules by extension. So it naturally maps to endomorphisms of M for all M in ind-co of R. So you have a natural map from this ring, this Hochschild cohomology of ring of R, into the ring of endomorphisms of any object in ind-co of R. So, right. So then what you can ask is, so if you're given a homogeneous ideal in here, then you could ask that when you invert those elements on M that you get 0. So you can make the same kind of definition as before. Okay, so this is something that you have in general. So, right. So for any homogeneous ideal in the Hochschild cohomology of R, so you can define a subcategory of ind-co of R, and explicitly it's going to be those M such that M adjoin 1 over F. So such that if you look at any of these operators that you get coming from the ideal, you invert them, that you get 0. All of them. So this is something that you can do. So this is an observation that you can do in any presentable stable infinity category. If you look at the Hochschild cohomology ring, and if you have a homogeneous ideal in the Hochschild cohomology ring, then you can use that to define a localizing subcategory. And when you look at all M such that when you invert those operators, you get 0. Well, when you invert any element of an ideal, you get 0. Okay. So this is kind of same. And then I guess the point is that right. So structure. So then the construction is that if you look at this thing of Z, and then you take function on sign of Z, functions on a sign of Z. So this is a graded ring because this is not a problem. So basically, it's just that symmetric algebra, more or less. This naturally maps to the Hochschild cohomology ring in such a way, well, it's respecting the grading, so such a way that like degree 1 classes here are going to degree 2. So map of graded rings, I guess multiplying the grading rate. I think this is some version of the actual Costan-Rosenberg isomorphism. Okay, and then that's basically it. So you have this map of graded rings, and we've seen any homogeneous ideal of the Hochschild cohomology of R. That's going to define a localizing subcategory of ind-co. And then you have this map of graded rings. So whenever you have a homogeneous ideal over here, that's going to cut out a localizing subcategory of ind-co of R.
How is the Hochschild cohomology here supposed to generalize the cohomology of PG? Like this is the same example from the PG one that you put it to us.
Yeah, it's more or less the same construction, except so in that case, it was also simpler because you had this natural tensor structure, a lot of endomorphisms to the unit, and then you could use that to get endomorphisms depending on. But here you're just saying like let's just look at all endomorphisms of the identity structure. So this thing that sort of tautologically is going to act on everything. And then you make the exact same thing. Okay, so that's basically just thanks. Any questions for the speaker?
What was your comment about the
localizing subcategories here, that's it. Like, can you repeat that comment? Like you,
Which comment?
so I guess I don't see why you considered all m such that m1 over f equals 0.
Well, sorry, so I mean, this is a definition, I mean, this is a definition of a localizing subcategory. I guess, right, I mean, this is sort of analogous to the idea is that this is sort of analogous, right? So that there was an earlier example, you can look at all objects in D of Z such that when you invert P, you get 0. And this is sort of a more elaborate version of that, except that the operator that you're inverting is not like in degree 0, right? So I guess the main difference is that instead of inverting P, you're inverting an element of the ring, you're inverting an element that is like one of the focal function on this space thing of C. So this is giving you, so in this case, the point is that F is living in degree in some positive degree. But so, right, so inverted. So I'm not sure if that was the answer to your question.
So this construction we made, yeah, I guess I don't know how to ask.
Yeah, I mean, sorry, so maybe I should have just written that sort of explicitly. So, sorry, so here's the general thing that probably should have said earlier, is general. So if C is a representable table affinity category. So then you can define the Hochschild cohomology of C, and then any homogeneous ideal I sitting inside the Hochschild cohomology of C. So the Hochschild cohomology of C by definition, these are endomorphisms of identity vectors, so they act on any object. And it's going to define defines the subcategory, a localizing subcategory. Let's call it C sub I. And right, so this is, so we should think of this as like objects that are sort of supported on the analog of quasi-smooth routines and speculating supported on this. And by definition of this is all and C such that for all F in the ideal I, and then well, I should say F homogeneous. And so if you have a homogeneous element in the ideal I in Hochschild cohomology, then it acts on any object M by shifting the grading. This is the construction that you can make, that you can define a localizing subcategory for any presentable group. And right, so the point is that in this case, the Hochschild cohomology of the ring receives a map from this ring of functions on things. I think that's right, yeah.
So in the classical theory of D modules, there's this notion of singular support, which also lives sort of in the cotangent bundles, sort of subvariety. Is it named in analogy with that? Is that what's going on here? But there's no,
I think so.
there's no flat connection analog here. Maybe I'm wrong. Am I?
Well, I guess here we just have an object of ind-co. But I guess right. So I guess the way that you would define a singular support for a D module is maybe not quite this way.
I see.
So you would choose a filtration and then right, because you would choose some sort of filtration on your D module and then associated you get something literally on the filtration bundle. And okay, so I don't know
Yeah, how to do
but at least it seems like it seems to be a different.
I see.
So if C is the category spectra, like how can I put the Gaussian position in this context? Is that like if it affects some homology? Like what would be the ideal?
Yeah, so I guess this isn't really gonna give, I mean, I guess, right, so this construction isn't really gonna give you the, like, well, so the point is that in spectra, you get a lot of, objects, you get a lot of additional. So in spectra, you could, this would, I think, it's not gonna give you anything so interesting, it'll give you like the subcategory of p power 20. But if you want to define, for example, like subcategory of like LNF acyclic spectral, then it won't be defined in this way. It's not really defined by well, I guess, sorry, so maybe you could define it, but you would have to define it in duct. Then, sorry, I'm just saying like the Hochschild homology of all the spectra is not going to be the sphere. But maybe if you take the Hochschild homology, like it's like a p tortoise. You know, sorry, I'm still not seeing how you would.
So just to clarify, the one last question there, so you have this Hochschild, this Hochschild homology, which is a natural map to the endomorphism of M, and you say for any I, we can define this subcategory,
Yes.
and you use that to construct this map when you gamma sin Z O to, so.
No, sorry, this is a separate construction. This is basically the HKR, this is some version of the HKR
Oh, I see, so those are different, this is not explaining how to, okay, sorry.
No, sorry, I just lost over that.
I see, okay.
Sorry, yeah, I guess the other thing to say, so your question, right, there's no claim that this is gonna give you all the localizing. Well, I mean, or even like yeah. I think, right, so okay, C is like compactly generated, something then these things are gonna be compactly generated. So that'll be one, but it's definitely not necessarily gonna give you all compactly generated localizing. There's sort of some cases where it does, but perspective.
Questions? Comments, thoughts? All right, let's end this.